So we had started already discussing about Tomita's theorem, Tomita's main theorem, in the context of, although we stated it in the context of one-dimensional algebras and indicated the general results, but we could only prove it for matrices so far and states on matrices. Okay. So just to remind you, what were the players in this? You had R, a one-dimensional algebra, and U, so acting on, let's say, Hilbert space H, acting on H. And then you had this vector U, which was a separating and cyclic vector, separating and generating vector for R. And the idea was that since it is separating and generating, what you have is RU. So this is norm closure of this. So all those operators in R acting on U. So this is in fact equal to H, and the same goes for R prime. We had seen that a vector is separating for R if it is cyclic for R prime or generating for R prime, and vice versa. So you do have this is also equal to H. And based on this, you were able to define certain operators on RU. So this is now a dense subset. In the matrix case, it would be the whole of it, to R of U in the following manner. So you had SAU equals A star U. And similarly, you had another operator F, which was from R prime U to R prime U, which was given by F of A prime U. So A prime being in the commutant equals A prime star. And one of the things is that F is actually the adjoint of S, but for now, for the matrix case, I guess we can show it. So with a kind of question mark, we have to keep note that F is actually equal to adjoint of this operator S. This in the general case, it will be an unbounded operators. So having identified what we are missing, we had gone forward and mentioned Tomita's theorem. So we had said that we will look at this operator and do a polar decomposition. This is in fact S is a conjugate linear map. And this gave us this is positive and this is conjugate linear, isometric. And we had proven certain relations. As a quick reminder, it was, for example, you had things like J commutes with delta to the IT, and if you have a real number, then you have J of delta to the T is equal to delta to the minus T of J. So if you were to encapsulate this in this manner, so you'll have, if you use any complex number, for example, if you have IZ, then you would have so let's see, is this correct? So when Z is real, it is fine. So when Z equals T, this is fine. And when Z equals minus I, so you have a delta minus 1. So minus I bar is I. So maybe you should have a minus 1 here. No, sorry. So let's check that. So how do I write it in general? So if Z equals I, then you want to say delta minus 1 is equal to delta of J. So this delta I should have as I times minus I, which is Z bar. Yes, so this is correct. So this thing is correct right here. So this is for any complex number for all Z in C. And similarly, you had delta of U is equal to U, you had S of U is equal to U, and so on. S star of U was equal to U, because we thought of U as identity acting on U, and identity was both in R prime. So keeping this in mind, then towards the end, we had started talking about the modular condition. So yeah, so the modular condition was essentially like if you have a group of star automorphisms, so star automorphisms of R, and let's say you have this state. So this is a state on R. Then this family alpha T satisfies the modular condition relative to omega if, so you have this function, so you have this function F, which is analytic in here in the interior, and continuous and bounded on the whole strip, on this whole infinite strip. F is continuous and bounded on the closed strip. So here imaginary part of z is equal to 0. Here on this side imaginary part of z is equal to 1. So these 0 and 1 don't really matter that much, as you will see. But in any case, this is the general idea is that you have this such that on this part, so f of t is equal to omega alpha t a b, and f of t plus I equals omega b alpha t of a. So somehow you have this portal which will twist this product. And let's say, for example, t is equal to 0. That means it's the identity automorphism. You have omega of a of b on this side. Let's say this is 0. You have omega a b. And then eventually you somehow transition to omega b a. Okay, but no statement. So I said it is somewhat giving you a twisted condition. Like a trace would say trace AB is equal to trace BA. So I had mentioned that this sort of modular condition is equivalent to what is known as a KMS condition, and which reveals that this is some sort of twisting of the trace. And this was the question asked by Shruti last time, like whether they are the same sort of condition. So so right now we'll just reprove what we did in the end, and we'll see that they're actually pretty much the same. Okay, in fact, the proof involved that step, and the midpoint at this point, when we approximated, like we had two different functions and they kind of matched up this here. So if you use the description from below, you will get something like, let's say omega AB. So I'll write the accurate statement, and something like omega B sigma IA on the other side. So this will be like the KMS condition. So omega AB being omega B sigma IA. But note that there we are taking only sigma t where t is real, right? Here we are talking about alpha t being real. Here there is no loss, because when we wrote this expression delta to the z r delta to the minus z, we had already realized that it could be any complex number, just that if I need a star automorphism, I need z to be of the form it. So we'll make the connection. That's the first thing we'll do. So let's try to reprove the last theorem. So what was that? It said that if omega u. So this is, note that u is a separating and generating vector. I'm just reusing this notation. So this is in fact a faithful, I'll put this in bracket, and anyway it's a vector state. So faithful normal state on R. So I don't need to write if. So in our notation, omega u is a faithful normal state on R. And so u was a separating and generating vector. So the theorem says that this modular automorphism group relative to omega, automorphism group, instead maybe I should say relative to u, or equivalently maybe you can say omega u, satisfies the modular condition relative to this state omega u. So in other words, what do we have to show? We have to show that omega u sigma t a of b. So you have, this is a function on one side. So on the other side, so anyway, I'm reflecting things around, but the modulo that it's fine. So you have this function, this is a function, a real valued function here on this side, and in between there is an analytic extension. There is an analytic extension that you can do between these two things. Extension from the boundary. So that is what we have to show. Okay. So now let me just write out this definition. Omega u sigma z of a. There I had a sigma t, instead I'll write as sigma z of a of b. Anyway, this makes perfect sense. And then what is the definition? This omega u for this vector state, the way it acts is you, so how have I defined my, okay, by the way, I have not told you what sigma z is. So the way I'm defining it, it is delta to the, should I take a minus iz? Yeah, so let me for the moment take delta to the minus iz, a delta to the iz. So this is my definition of sigma z, and as you can notice, if I put in a IT here or sigma t here, I see. So that's why I didn't have that. Okay, sorry. So I'll just put delta to the iz here, a delta to the minus iz, and note that if I put in a real number sigma t, it is just giving me delta to the it a times delta to the minus it. This is really the one I care about.
You can write sigma as A.
Right.
A is analytic.
If A is analytic. So here everything would be analytic. So this we have already seen that this makes sense for any A, right? Because we had this expression like from the motivation, although it was not a complete proof, at least for the MNC case, it's a complete proof. We had the Gardner's invariance theorem, which said if you have a similarity, then you have this analytic family, and it for any A in R, this will be analytic. Right.
Or maybe in some physiological context, then we have to define those things. So that
Yeah.
there are some dense algebra. Analytic elements form a dense algebra.
So what is the definition of analytic elements in the? Yeah. Okay. You have a.
Then that when T goes to sigma T A.
T goes to sigma T A.
Yeah.
So now this is in the context of a general C-star algebra. So you have this one parameter. Is it non-continuous sigma T? Strongly continuous. So you have a representation of the C-star algebra on a Hilbert space, and then you are talking about strong continuity.
No, I'm strong in the sense for each case we have this one side is already real number of points there. And that's the considering the number. So T goes to sigma.
Okay. I see. I see. I see. So for each A, it is non-continuous. For each A, it is non-continuous. Okay.
And extended to usually because the strip, or we can extend that to an entire function constant. If you can do that, then that element A is called analytic.
Okay. So if for example, if you so you have this sigma T A, and this is for only real T, right? Only for real T.
Yes.
So what you're saying is if I can extend, if there is an analytic extension of this, so you have this sigma T of A here. If there is some neighborhood on some strip, you can do that. I guess probably there is a theorem which says if you can do it for some neighborhood, then you can extend to all of C. Yeah, so here actually everything is analytic, right? Yeah, because here you are going with some arbitrary. So typically you deal with the inverse problem, right? I don't know much about KMS condition on C-star algebras, but from what I superficially see, the way it happens is first you have this automorphism group, then you try to find states which satisfy the KMS condition with respect to that. So here actually you are getting all of them together. So it's a very rigid kind of thing we're doing. We're starting with a omega u separate, generally a faithful normal state. Corresponding that, we are making a choice of a very particular, the modular automorphism group. And in that case, they are like best buddies and everything becomes analytic there. That's kind of the assertion here also in this theorem, right? So I'm guessing if you have a representation of the C-star algebra and you maybe look at its weak operator closure and see if things survive, if this, for example, this dynamical system is also a dynamical system there, then maybe one could argue, maybe, I don't know. Like, for example, do you know like a C-star algebra, like a C-star dynamical system where every element is analytic? Like, is there a characterization theorem? Okay.
Just a dense algebra that is in this that's not all analytic elements and
Okay.
elements.
So yeah, anytime you have strongly continuous thing, you have a dense subalgebra of analytic elements. Okay. Okay. Yeah. So for those who are online, I guess so Shruti, and since she works quite a bit on these objects, C-star dynamical systems, but there you start with a strongly continuous dynamical system, and then I guess you ask questions about what states satisfy this KMS condition with respect to that. And there typically you have this one parameter family, you want to extend this. And when you can do that, those are called analytic elements. But here we are getting it for free, kind of. Okay. So yeah, so sigma z of A, I have defined it for all complex numbers. So these computations, although the relevant ones will involve like sigma t, but we'll do it in general, and we'll see the connection with the KMS condition, which is more familiar maybe to the dynamical system people. Okay, so what does this look like? By definition, it is delta to the iz, A, delta to the minus iz, just writing out the definition. B u dot u, that's all. bu dot u. Now I can move this delta iz. This is actually the only issue that we have is we have to keep track of conjugate linear and these kind of things. But here delta is not such a thing. It's actually a proper linear operator. So when I move this here, I know that delta u is equal to u. So any function I take of delta, when I apply on u, you'll get u. So this is in fact equal to a delta to the minus iz du u. So I have moved the delta, but it doesn't really affect my u. Now what I'll do is apply j on both sides. J is a conjugate linear isometry. But if I apply j, I have to move things, shuffle things around. So I get a ju here. I get a ja delta to the minus iz bu here. Okay. Now the thing is, I don't know how to really work with j, but I do know how to work with s, because s of au gives me a star u. So what I'll notice is that s by definition was j delta to the half, and it was in fact delta to the minus half j. So the description of this I'm going to use is delta to the half s is equal to j. So delta to the half su, and here maybe, okay, maybe I did it too early, sorry. So let me take this back. I did, because this ju is also u, right? So it's not very helpful to have the j there. So what I want to do is move the a first. So I have a delta minus ij bu a star u. I have this. Now I'm going to apply my j. So I have a j a star u and a j delta to the minus iz bu. Now I'm going to apply delta half s, but s will make a star u into au. So I get a delta half au here. And then here, j delta to the minus iz, we had noted what is the condition. So that should be, so j delta of minus iz. So in fact, I'm replacing z by a minus z, but bar doesn't really affect that. So I'll get a minus iz bar here. So this will be, there is a delta to the minus iz bar and j of bu, but j again is delta to the half sbu. So all in all, I move this delta half to the other side. It's a positive operator. So I get a delta 1 plus iz bar au, and this is a b star, simply because I have applied s on bu. So this is what I get. Now, if you compute omega u of b sigma z u, sigma z of a, what do you get? Same story. We'll write b delta to the iz, a delta to the minus iz. Here, what do we have? This is u dot u. So you move the b star, and this delta to the minus iz doesn't matter because delta u is equal to u. We have seen this. So it gives me delta iz au is equal to b star u. So these two actually look quite familiar, similar, right? You have a au here, you have a au here, you have a b star u. It's only that the z is different. But what does that mean? I can transform my z appropriately. So for example, if I replaced my, so again, it's just a matter of dealing with the right complex numbers. So what do I substitute here? Okay, so now instead of dealing with complex numbers, let me deal with, if I assume z equals t, for example, omega u sigma t a of b is delta to the 1 plus it au b. There's a b star u, right? Yeah, b star u. And omega u, so this, and here I have a iz. Okay. So b sigma z a is equal to delta to the iz au. So somehow I need to pick z such that these two match up. So how do I pick my z? So I want to solve iz equals 1 plus it. So the imaginary part of z is equal to t. Real part, I mean real part of z is equal to t, and imaginary part minus of that is equal to 1. So what So I should pick something like t minus I, right? So I'll pick z equals t minus I. So what do I get? Omega u b sigma t minus a is equal to delta 1 plus it au b star u. So now we get something which will look more like an equality. Omega u sigma t a b is equal to omega u b of sigma t plus I a. Now, if I put in t equals 0, what do I get? I get, so sigma of 0 is the identity. So omega u of ab is equal to omega u of b of sigma I of a. This is the more familiar looking KMS condition, right? So here is the twist that is happening. And then ideally, if this is trivial, then you would have omega u ab equals omega u ba. But here it is telling you, although it's not a trace, but how similar does it look? Okay. And if you maybe look back at the proof very hastily that we had done towards the end, effectively, it was this step only. The thing was we defined two different functions, one from 0 to a half and a half to 1. Then we had shown that it is compatible in here. But really, this computation, this equality computation is happening on this midpoint. So you're approaching it in a different definition. You're approaching it from a different definition here, and both of them match up in here. So it's really the same thing. Okay. So yeah. So you can look back at the proof, but yeah, so we can just go one step further and have it for, so here you have sigma t minus I, then you can substitute maybe t minus I yeah, here, and then you will get a 2I. So the strip will be of size 2, and then you will get this analytic function that we're looking for. Okay, so now we know that, so if you have a separating and generating vector, and then you have this corresponding state. So the modular automorphism group is something special, but there is still some part remaining. So here we said that the modular automorphism group satisfies this modular condition relative to omega u, but in fact, something stronger holds. In fact, this is the only automorphism group, like a continuous one parameter family, which satisfies the modular condition relative to omega u. So that proving that will take a little bit of effort. But before that, let's look at some consequences. So suppose omega is any state. So suppose omega is a state of R, R being a von Neumann algebra, and alpha t, so t in R is a one parameter family. So it's a one parameter group of automorphism. Group of automorphisms of. So by this, strongly continuous, and in the sense that if I pick any element of R, alpha t of R, you have a non-continuous family of operators. Yeah. So that's what, so the topological things are hidden, but that's what we mean by one parameter groups. So star automorphisms, I should say, star automorphisms of R, that satisfies the modular condition relative to omega. Okay. And let's say H is in R. So what do we have? We have a von Neumann algebra. We are not talking about any separating generating vector here anymore. We're just saying we take any von Neumann algebra and we take any state. It doesn't have to be a normal state or anything like that. Then we have a one parameter group of star automorphisms that satisfies the modular condition relative to omega, and you're choosing some operator H in R. So of course, the results will involve this operator H. The first thing is that omega is invariant under these automorphisms. So omega is invariant under alpha t, in the sense that is omega of alpha t of A is equal to omega of A for all t in R. Omega is invariant. Second thing is that if you have an operator which is invariant under alpha t, so if alpha t of H is equal to H for all t in R, then omega AH is equal to omega HA for all A in R. So if this is kind of the fixed points, the common fixed points for all of these automorphisms, H, then this kind of behaves like a trace. It's just saying that omega of the commutator A and H is equal to 0. And if this were true, let's say all these automorphisms are trivial, then what you would have is omega of AH. So essentially it would be trivial state. So 3 is if omega is faithful and omega AH is equal to omega HA. So effectively you want to reverse this arrow. Here you said if H is invariant under alpha T, then omega H, so omega behaves like a trace. You want to reverse this, but that is only possible if you are assuming omega is faithful. So if omega is faithful and you have this for all A in R, then alpha T of H is equal to H for all T. Okay. And then number 4 is again, if omega is faithful, that's a very quick corollary of part 3. Then alpha T leaves the center alone. So all these anything which satisfies the modular condition cannot move the center at all. So this is for all T and R. And C in the center of R. So 3 implies 4 should be immediate. So let's see. So if omega is faithful, yeah. So because if H is in the center, clearly you have omega AC simply because AC is equal to CA. So it's a quick application of 3 that the center is left alone. Right, okay. So now we start with this H and let's say omega AH is equal to omega HA for all AA in the one Neumann algebra R. Now, this is true for all A. So in particular, it is also true for this. Actually, I should say in general, not in particular. So for all T, you have this, right? I'm just replacing A by an alpha TA. Now, what does this say? We have that the modular condition is satisfied. So if I take any pair of operators, I should have that. So I have an analytic extension. So this part is omega alpha T of H. And this part is omega H alpha T of A. Okay. So then what do we have? So let's call this function, this analytic extension F. So what we have is F of T is equal to F of T plus I. Right? So F of T is equal to F of Ti plus all T in R. Now this is a continuous and bounded function. Now what I can do is reflect this function around this. And since it is compatible, I can have the definition, it will again be an analytic function. I can in fact extend this F to all of C. So extend F, I don't know what's the, maybe by reflection or something. Okay. Extend F to all of C, you understand the procedure. So hence you get a bounded continuous function, which is holomorphic on, so you get a bounded holomorphic function on all of C, and by Liouville's theorem, you know that it's actually a constant function. And get a bounded holomorphic function on C. So by Liouville's theorem, the whole function is constant. So in particular, you have F of T is equal to, like on the whole strip, it's a constant function. That's what we have. So what did we want to prove? So now let's look back. Yeah, so if alpha T of H is equal to H, so omega of alpha TA H is equal to omega A alpha So with this observation, what do we have? So we want to prove that omega is invariant under alpha of t. I want to say that this is actually equal to omega a. Yeah, right. Yeah. So what we concluded is f of I, for example, is equal to f of t plus I for all t, right? Because it is constant here. Initially we had that it is constant, like equal across this, but using Liouville's theorem, what we have is it is constant across this. So just looking at this line, so here at 0, you have omega AH. Then at time t, you have omega alpha t A of H. So by the constant, the fact that it's constant, you have this equality. This is true for all t in R. Now, putting in H equals identity. So for H equals identity, what we have is omega of alpha t of A is equal to omega of A. Yeah, so yeah, simply because this condition is satisfied. This is the assumption that we had. Assuming omega AH is equal to omega HA for all A, we had concluded that omega alpha T A times H is equal to omega AH. But of course, H, like identity is in the center. So you do have that. Okay. So part 1 is done. Now, what about part 2? Okay, part 2 is a little bit more involved. Let's finish part 3. And we saw that part 3 implies part 4. So part 4 is an immediate consequence of part 3. So here we have assumed that omega is faithful and omega AH. So we want the reverse conclusion. So this is true for all A in R, and H is fixed. So H is fixed. And we have this for all A in R. What you want to conclude is alpha T of H is equal to H. Yeah, for all T. Okay. So now omega of alpha TA times alpha T of H, simply because alpha T is a star automorphism. So you just have this, and we just proved that this alpha T I can remove. This is equal to omega AH. And then again, we have proven here, this is equal to omega alpha TA times H. So what is the conclusion? Forgetting the middle steps, we have omega of alpha T of A times alpha T of H is equal to omega alpha TA times H. Okay, so putting this together, what we have is so alpha TA times alpha TH. Yeah, so this is equal to 0 for all A in R. In particular, I can put in alpha minus TA also. Like if you give me a T, I can put, so I don't need to carry this alpha T. So what I have is omega A 0 for all T in R. Up to here, I have not used the faithfulness of the trace, right? Of this state omega, sorry. So here, all I need to do is look at its adjoint. So if I have omega of AB is equal to 0 for all T in R and A in this 1/1 algebra R. Yeah, so all I need to do is put this adjoint. So then you will conclude, so this implies alpha TH minus H is equal to 0 using faithfulness of omega. Okay. So now what remains is part 2. So what was 2? So 2 says that if alpha TH is equal to H, then you have this sort of tracial condition. So number, yeah. So the assumption is that alpha T of H is equal to H for all T in R. Now look at this function G of T, omega alpha T of H times A, which is the same as omega HA. We have proven that. And then look at G of T plus I, which is equal to omega AH. So this follows from this fact, omega alpha TAH is equal to omega AH. No, sorry. So that's what we want to prove. This was under the assumption that omega h is equal to omega ha. So sorry, I take that back. So how do we have this? Oh yeah, simply because the assumption here is alpha th is equal to h. So just replacing alpha th with h. Okay. So you have this g of t, you have g of t plus I. Our goal is in fact to show that g of t is equal to g of t plus I. Now this is saying that g of t is constant, right? On the real line. So g is constant on the real line, and so also it is constant on the whatever this line with imaginary part equals 1. So on this and this, it is a constant function. So I can multiply it with some scalar to make it a real number, right? G, and again the holomorphicity and all of that will not be affected. So without loss of generality, assume G is constant real number on R. Now, by the Schwarz reflection principle, you have this analytic function which is real on this, so you can actually reflect it. So you have this is real valued here. So you use the Schwarz reflection principle, and then do the same technique as we did in the first thing. So there we had used Liouville's theorem by the assumption that these two were equal. At that point, we had been able to reflect things around. But here, simply by the fact that this is real valued, we can reflect this and keep doing it until so until we cover all of C. So Schwarz reflection principle gives a analytic extension to all of C, which is bounded. Hence, using Liouville's theorem, you have g of t is equal to g of t plus I, which means these two are equal. Okay, so here we didn't need faithfulness. Okay, so this kind of tells us that, of course, there's so much intimate connection between this automorphism group, so much invariance that is going on, like alpha t is omega is invariant under alpha t, and if something is left fixed by all of these alpha t, the tracial condition is being satisfied in a way. Okay. So here's a quick corollary. So same assumptions, omega is a state of a von Neumann algebra. Algebra R, and alpha t, so one parameter group of star automorphisms of R, star automorphisms of R that satisfies the modular condition relative to omega. Okay. So here the conclusion, the two. So if each alpha t is identity, so equal to identity automorphism, which means everything is stabilized by this. Everything is invariant under this. So what do we see from the first condition? If h is left invariant by all of these alpha t's, then omega h is equal to omega ha. So for example, if alpha t were all of them identity, then this is true for all h, which means this equality holds for any a and h. So if each alpha t is identity automorphism of R, then omega is a tracial state. The converse, you want to use number 3, right? So to make such an assertion, so you want to say if something is left invariant by all of these alpha t, so if omega is faithful and tracial, then you want to say alpha t leaves all this invariant. So you want to prove a converse, but you need faithfulness for that. So if you have omega is faithful and it's a faithful tracial state, then all these, anything that satisfies this modular condition has to be trivial. So if omega is a faithful tracial state, then alpha t is equal to identity automorphism for all t. Anyway, there is not much to prove, just a matter of reading of what these things mean. So this also kind of tells you that when we are talking about discussing like the basic Tomita theorem in context of matrices, choosing the trace was a bad idea because we are getting only trivial things. This modular automorphism group is trivial, and yeah, not much interesting things are going on. But if you choose non-trivial state, you do get a modular automorphism group, even in the case of matrices. But things actually start getting more interesting when you move on to, like we have been repeating, like when we move on to type 3 factors, which don't even have a faithful, like normal semi-finite trace. Okay, so we'll get there. But based on these theorems, we make a definition. The centralizer of a state, omega, on a C-star algebra is defined as, so defined to be, so C-star algebra, let me denote it by an A. So the centralizer of A with respect to this omega is the set of all H in omega, such that omega of this commutator is equal to 0, or in other words, omega AH is equal to omega HA. And this is true for all A in H. For example, if omega is a tracial state, then the centralizer is the whole one-member algebra. Otherwise, it is going to be a subalgebra. You can see that if you have omega AH is equal to omega HA, this is true for all A, then you can take stars. So omega, these are star preserving maps being states. So that will also be true for stars. So if H is in omega